Yeah, so you are the host now.
Right. Okay. Shall we start or only I think how many people? 12 people has joined, or 10 people has joined.
Yeah, we can start.
Okay, fine. Yeah, good evening, everyone. Till the last class, we have seen the modeling of the grid, modeling of the generator, and we have seen what are the different options that are available in the ETAP, how to create the single line diagrams, what are the different methods of creating the single line diagrams. All those details we have seen in the previous classes. Now, today we will focus on a new topic, that is the transformer modeling. So as far as the ETAP, not only the ETAP, but any other simulation software is concerned, the modeling of the transformer is a very important. Modeling of the transformer and modeling of the load. These two are very important. And you should know basics about these equipment, especially. Why? Because the transformer is one of the major equipment in the electrical power system. So for every system, whether it may be the transmission, distribution, whatever it may be, you may need this transformer. So the transformer modeling is important. So today we'll start with the transformer modeling. I hope I am loud and clear, right?
Yes, sir.
Yeah.
Yes,
So
sir.
in the
Clear.
transformer modeling, we will be discussing on the applications of the transformer. First, I will try to cover some basic concepts related to the transformer modeling. Then we will switch over to the ETAP and we will see the different options that are available in the transformer for the modeling purpose. Okay, right. So in this session today, we will be discussing on the application of the transformers. What are the different standards? Let me note it down and we will cover one by one. Yes. Show the screen. Right, fine. So in this today's session, we will try to cover what are the applications of transformers.
Sir, please zoom.
Yes, sorry.
Please zoom the Excel, sir. So easily you showed.
Yeah. Is it visible now?
Yes, visible, sir. Thank you, sir.
So we'll start with the application of the transformers and what are the standards that are applicable for the transformer. And I will just touch upon the equivalent circuit of the transformer, in which we will will give a brief about the open circuit and the short circuit. And what is the purpose of conducting the open circuit and short circuit? What are the important parameters that you will need to note it down from the results of the open circuit and the short circuit test? And then we'll proceed with the modeling of the transformer. Precisely, if you ask, it will be the modeling of two-winding transformer. In this, we will see the different types of coolings. What is the importance of the altitude factor? Altitude factor and the temperature derating factors. Means with increasing the temperature, how the transformer will get derated. What is the concepts behind that? So that probably we will see. And then we will discuss about the impedance and its tolerances allowed for the transformer as per the IEC 60076 part 5. And then at the last, we will see the VLTC range, means how to select the VLTC ranges, on-load tap changer, whether it may be the fixed step or it's the with the help of the AVR, means the automatic voltage regulator, and how to do the tap optimization. And then we will see some load flow study cases with the results. Okay. So these are the topics which I am going to cover as far as the transformer modeling is concerned for the ETAP. So I hope this is clear, right?
Yes, sir.
Right.
Yes, sir.
Yeah. So first, let's start with the transformer applications of the transformers, especially. Right. So let's start with the application of the transformer. Can anyone say like what are the applications of the transformer, or what is the purpose of the transformer? Any ideas? Any answers that I can expect?
Step up and step voltage regulation provides, sir.
Yeah, that's the okay. We can write it out step up or step down, right?
without
Yes,
change
sir.
the frequency, sir.
Sorry.
A step and a step down without change the frequency.
Yes, yes. And then
Also,
anything else that you
the
are- huh?
voltage regulation, sir.
Yes, okay.
Reduce the fault level of the substation.
Sorry, the fault level.
Reduce the fault level, correct, sir.
No, see, I'm asking about, okay, one way you can, to limit the fault current, you can say, right?
Yes, sir.
Yes, sir. Yeah, limit the fault, correct. Yes.
And anything else? Okay, fine. So, first one is the step up or step down the voltage. So that is the main purpose of the transformer. That means the transformer will transfer the power from one voltage level to another voltage. Okay, in this, it will helps in this isolation also, means isolation transformers, right? So it provides the electrical isolation also. Then it converts the three-phase three-wire system into three-phase four-wire system, right?
Yes, sir.
It converts three-phase three-wire to three-phase four-wire, especially for the lighting and the welding applications, where you need the single-phase power supply. Okay. Next one is to limit the short circuit or to limit the fault current. Needless to say, using the transformer impedance, it helps to limit the short circuit current as well, right? What is the typical example is the unit transformer and the lighting transformers. Unit transformer and lighting transformers. So these are all the typical examples of the transformers which we will use to probably limit the short circuit current. Okay. And definitely with the help of the OLTC, we can regulate the voltage of the LV side voltage of the bus. So as I told you in the previous class also, the OLTC or the tap changer that you are provided in the transformer is not only to help for the voltage regulation, but it is useful to extract the maximum reactive power capability that is available in the generator, right? So that is also another purpose of this. Anything else? To step up, step down the voltage, isolation, converting three-phase three-wire to three-phase four-wire, limit the short circuit current. Anything else? Harmonic mitigation. So basically to suppress the few harmonics, not all the harmonics, but the balance of balanced third harmonics and the multiple of third order harmonics. If you go with a normal delta star transformer, it eliminates the third and the balance of the third harmonics. And for this harmonic applications, the type of transformers that will be used of the K-rated transformers for the harmonic applications. That means if you are using the transformer in the applications, which is having, which will generate a higher order harmonics or higher harmonics, there is definitely an additional heat the transformer should be able to withstand. So for that, we can go for a K-rated transformer. Okay, of course, we will see. This in the ETAP also, I think it is available. So wait, yes. You see the transformer here. So in the transformer, if you go to the harmonic, so here there is a factor called that is the K factor. So this K factor is generally used for the harmonic applications. Like if the transformer is being used for a application where like arc furnace applications where you are having a very higher harmonics or harmonic rich applications. So then the additional heat will be generated due to the harmonics. So a transformer should be able to withstand that harmonic, withstand the heat or withstand that temperature due to the harmonics. So in that case, we will go for the K factor transformer, or you will call it as a K rated transformer. You have different varieties like K factor 1, K factor 4, 9, 13. Similarly, the K factor will be considered when you are using the transformer for the excitation system. Like in the generator, you are having a voltage regulation, right? Through the excitation system. So your excitation system is having a set of converters. So which will generate which will generate a fifth and seventh, predominantly fifth and seventh order harmonics. So for that applications also, you will use this K factor or the K rated transformers. Okay. Next.
Sir, what the value indicate the different value of the case, sir?
Yeah, that we will see. That we will see. So if you like, let's suppose if I give the rated transformer as of suppose 10 MVA transformer, and when selecting this K factor here, if you see here, just observe this. When the K factor is 1, so the I current means I total is 100. What is your rated current of the transformer? That is also 874.8. Right. Now, if I increase this K factor to, let's suppose K factor 4, now your transformer will be, oversized. Means it will be oversized to 125.8%. Okay. By the way, if you increase the K factor, so the transformer that it is getting, it will able to handle much current. Okay. So if K factor is 40, it can able to withstand.
So what is it? Hello, sir. In this case, we are changing the K factor. We are totally percentage, high total percentage is increased. What is the rated current?
So rated current is to 874.8, right? If when you include the K factor, it can able to withstand 2696 amperes. Okay. If the K factor is 4, normally when the K factor is 1, that means the transformer rated current is 874.8. But when you introduce the K factor in the transformer can able to withstand 1100 ampere rated current.
That is additional.
Yes. That means your
Additional
transformer is getting oversized. Yes, exactly.
Yeah, thank you.
Okay, clear? Your MVA rating will not increase, but yes, your
Yes, sir.
current rating, that current handling capacity will increase. That means it will increase the conductor size. Basically, in the transformer manufacturing set, they will increase the conductor size to withstand this much amount of current. Okay?
Yeah, clear.
Yeah. Next one is the impedance matching transformers. Have everyone heard about this impedance matching transformers? So impedance matching transformers is one application. Means if you have some impedance and if you want to convert that impedance to some other impedance, then probably we can use this impedance matching transformers. So basically the impedance transformer will not match the impedance of two different transformers. I'm not explaining in that perspective. So what I'm trying to say is, if I have a load, the load resistance is say 10 ohms. Let me open here. Yeah. Suppose if I am having a load, or I will directly note it down, that will be better. Yeah. Suppose if I am having a load, the load, let's suppose the load resistance is 10 ohms. Okay. If I want to convert this 10 ohms to say example 10,000 ohms, for example, 10,000 ohms. So, or it may be, or I want to convert it to 0.01 ohms, whatever it may be, then this impedance matching transformer will help. What it does, it converts the impedance on the one side of the transformer to the other side with a different value. And ideally, you are doing the transformation of the voltage. If you take the application of the impedance transformers, impedance matching transformers, generally the applications are the audio transformers being used in the amplifier applications. So basically they are helpful to convert one impedance to another impedance. That is what the purpose of this impedance transformer is. And another application as far as our power system is concerned, that is the neutral grounding transformer. Neutral grounding transformer of the generator. That is also an impedance matching transformer, right? So basically this impedance matching transformer will be helpful to convert one impedance to another impedance. That's what the purpose of the impedance matching transformer, right? If you are not really understand the purpose of the impedance matching transformer, I will give you a very quick details to you. Let's suppose you are having a generator. You are having a generator and the generator fault current, if suppose I want to limit it to, let's suppose this is a 500 megawatt generator and the generator rated voltage is, let's suppose 21 kV. Okay. Now I want to limit the fault current of the generator. So for that, what I will do, I will use a neutral grounding transformer. So here I will use a neutral grounding transformer, and on the secondary of the side of the transformer, I will put a resistance. Okay. Suppose this is a 500 megawatt 21 kV transformer. Let's suppose if it is a 500 megawatt 21 kV transformer. Okay. And so this is the line to line voltage. So what will be the phase voltage? Phase voltage will be V phase equal to 21 kV divided by 1.732. So this is the voltage, phase voltage of the generator, right? Suppose I want to limit the fault current to, let's suppose 10 amperes because of the core damage core of the generator. So what will be the resistance that I needed? That is equal to 12124 divided by this current, that is 10 amperes. So I need the resistance of 1.212 kilo ohm, which should be able to withstand this much amount of the voltage, right? So your size of the resistance will be very high. To limit the fault current to 10 amperes, if I directly use the resistor, the size of the resistor bank will be very high. So for that, what I will do, I will use an impedance matching transformer. Let's suppose it is 21 kV by 240 volt. Okay. So if I convert this resistance and I will put, let's suppose, you can say yes. What will be the secondary resistance that I needed for this? That is equal to, this is the resistance, right? Into 240 volt into 240 volt divided by 21 divided by 21. Okay. And this divided by 123, 123. So this is the resistance which I needed on the secondary side of the transformer. So if I use an impedance transformer, I can put a secondary resistance of 0.1583. So with this, I will be able to match this resistance of 1.212 kilo ampere, 212 ohm on the primary side. That means on the 21 kV side of the transformer. So this is the purpose of the impedance matching transformer, right? So this is one application where you can use this, right? I hope this is clear. This way also we can see in this. Yeah. Let's suppose you are having a transformer. In the grounding, we can see. So here there is an option for the transformer resistor. So on the primary side, we can put a resistance, suppose let's say 21 kV. And you want to limit the primary current to 10 amperes. Okay. Let's suppose here the voltage ratings are coming down. Suppose if I put a secondary resistance and if it is 100 kVA, so what is the secondary ohm? That is 0.000313. So this is one application of the transformer, that is the impedance matching transformer. Okay. I hope this terminology is with respect to the impedance. Okay. If you have a different impedance and this transformer will convert from one impedance to another impedances. Okay. So here the impedance it is 0.1583, with which it converted with the help of this 21 kV by 240 volt transformer. It converted the resistance or the impedance of 0.1583 to 1.2212 kilo, 1.212 kilo ohms on the primary side of the transformer. Right. Next application is the zigzag transformer. So basically, what is the purpose of the zigzag transformer? This is to convert the ungrounded system to grounded system. Okay, that's how I can tell it as a application of the zigzag transformer. Next is the instrument transformers. because these are the different applications of the transformers where we may need to do the modeling in ETAP. Not only in ETAP, you have to model in the Dixon Power Factory or the PSCAD, whatever it may be. Okay, so these are the different applications of the transformers. And you have one more transformer that is called the phase shifting transformers. Basically, these are will be useful to increase the power flow in the interconnection area network. Phase shifting transformers. Okay. Right. And another is the rectifier applications. That means you can say it is the rectifier transformers, where you can use for the single, 6 pulse applications or the 12 pulse applications. You can use this transformers. Okay. Right. So this is about the applications of the transformer. I hope this is clear. Any doubt in this?
Sir, here we use phase shifting transformer, sir.
Prakash, can you speak a little bit louder? I'm not able to.
Sir,
Listen,
where
yeah.
we use phase shifting transformer, sir.
So phase shifting transformers, as I told you, this is generally used to increase the power flow in the network, like in the interconnected network. Then this phase shifting transformers could be used. Of course, globally, the current itself, the count of this transformer itself is very less. So basically, phase shifting transformer is a specialized type of transformer, typically used to control the active power flow. We know the formula, right? P equal to EV by XS into sine delta. Right? So if you control this delta, the P changes. So that's the purpose of the phase shifting transformers. Okay. So with the help of the phase shifting transformer, so they will able to manage the delta so that the power flow in the interconnected network will be increased. Yes.
Okay, sir.
Right. Fine. So this is about the applications of the transformer. Next, coming to the standards of the transformer. So we know there are many standards, but as far as the transformer is concerned, we are trying to focus on the standard that is IEC 60076. Okay. So as a part of IEC 60076, I strongly recommend you to go through at least some key important points of the IEC 60076. Let me ask the question, IEC 60076 consists of how many parts? If you know how many parts of IEC 60076 has? Any idea?
12 or 13?
No, sir.
IEC 60076. Suppose if you see with the IEC, yes. If you see here, so this is the IEC website, IEC web store. So if you see the IEC 60076, so you have a different number of parts, very number of like part 1, 2, 3, 4, 5, 6, 7, 8, 9 is obsolete, 10, 11, 12, 13, 14, 15, 16, 17 are obsolete, 18 is there, 19, 20, 21, 22, 23, 24, 25, 26. That means up to 26 in IEC 60076 itself, we are having 26 number of different standards in IEC 60076. Of course, some of the numbers have been already obsolete, so they are not mentioned in this document, in this website itself. Okay, but as far as our transformer application is concerned, we have to focus on the IEC 60076 part 5. Okay, so this 60076 part 5, it will give the typical impedance. This is IEC 60076 part 5. So this IEC 60076 part 5 gives the typical or minimum impedance values. Okay, just 1 second. Let me share the document. Just let me search. I think if I have, I will share it with you. Just 1 second. Give me. Yeah, let me share my screen once again. Yes, I hope the document is visible, right? So this is the IEC
Yes, sir.
60076 part 5 document. So as I mentioned, this IEC 60076 gives us the, let me go to the particular table number. Yes. This is the table which I probably want to tell you. Yes. So if you see here, this IEC 60076 part 5 table 1. This is very important. So this gives the typical or minimum impedance values. So this is one of the important aspect to start with optimizing the transformer impedance, right? So if you literally do not know how much impedance is needed, rather than starting with some unknown value, you can probably start with some well-known value. That's the reason why this is given. Okay, so this 60076 part 5 has been updated in 2006, but still the problem with the ETAP is they are following the ETAP 1992 version. Up to 21, I am telling you, they are still following the 1992 version of the 60076. So this is one important aspect of what you need to really look into. Okay, so this gives us the minimum impedance or the minimum short circuit impedance required for the transformer, depending upon the transformer rated power. Suppose if you don't have the transformer impedance and you don't have the transformer data sheet with you, and if you want to do the short circuit analysis or the load flow analysis for a particular system which is having a transformer in which you are not having the data sheet, so that time you can use this standard 60076 and particularly this table you can use it. Okay, right. Next, there is one more yeah, as I am telling you in the ETAP, let's suppose this is the transformer which is rating of 10 MVA. Okay, 10 MVA, and if I select the typical impedance, it is coming 8.35. Okay, so the typical impedance of the transformer that is coming as 8.35. Whereas if it is coming in this range, that means the 10 MVA transformer will come under this category, right? It will come under the, it will be above 6301 to 25 MVA. Up to this transformer 25 MVA, the minimum short circuit impedance required as per the IEC 60076 part 5 is 8.0. Whereas ETAP is using it as a 8.35. That's what I'm telling you. ETAP still follows the 1992 version. So probably they may be upgraded in the 24 version that I am not aware of, but till 21 I am sure that they are still using this 60076 part 5 1992 version, but not the 2006 version. Right? Clear. Next. So in addition to this part 5, there you have one more important standard, that is 60076 part 7. Okay. So in this, basically they will mention how the transformer overloading could be. How the transformer overloading could be. Let me get the document also. Six part 7. Okay. Yeah. So this is 60076 part 7. Okay. So in this, basically how the transformer is can be overloaded. Let me go to this. Let me go to the table in this. Yes. So yes, here this is the important table. Okay. So how this transformer overloading could be means how much time the overloading is possible is mentioned in the table 4 of 60076 part 5. So here we are classifying into distribution transformers, medium power transformers, and large power transformers. So if you have a distribution transformer, you can load this transformer even up to, if you see here, 2 times. So if you have a distribution transformer, you can load this transformer even up to 2 times for a short-term emergency rating. So they define short-term emergency rating as 30 minutes, I think. I think this document is not searchable, but somewhere in the document, if you can refer. So this short-term emergency is for the 30 minutes. Okay. So they may have defined somewhere in the upstream, but yes, finding it will be in the definitions. I think probably we will get that. Cyclic loading. Yes. So if you see here, the short-term is the emergency loading. So that is unusually heavy loading of the transient nature, less than 30 minutes. Okay. So that means the short-term emergency rating is for 30 minutes. So now if I go back to that table again, I think Nilesh, yes. So as per this 60076 part 4 or table 4. So if you go to the distribution transformer, so this distribution transformer can be loaded up to 2 times of the transformer rated MVA for at least 30 minutes. Okay. So if you take a distribution transformer, you can load this transformer to 2 times for 30 minutes and 1.8 times for a longer time. The long-term emergency rating is 1.8 times and 1.5 times for a normal cyclic loading and so forth. Similarly, if you take a medium power transformers and large power transformers, you need to probably understand this, how much percentage you can overload these transformers, right? And if you look at maybe one important aspect of the rating, let me get it one more standard, that is IEC 60076 part 1, because these three are interlinked basically. Okay, so if you see the part 1, so here in this, they have clearly mentioned where this IEC 60076 can be used, means where in which applications the 60076 transformer can be used and in which applications the 60076 is not applicable. So as per the 60076 part 1, if the transformer rating is more than 1 MVA, in single phase and more than 5 kVA, sorry, not more than 1 MVA, no, so more than 1 kVA. Yeah, and more than 5 kVA in 3 phase. Right. So, and it covers all the transformers, but at least one of this voltage is more than 1000 volt. At least one side of the voltage is more than 1000 volt, then only this IEC 60076 is applicable. Okay, instrument transformers, so their voltage will not be in this range. So that's why instrument transformers will not cover as a part of 60076. They will be covered as a separate part, that is 61869. Okay. Similarly, this 60076 is not applicable for traction transformers. Next is testing transformers, welding transformers, and explosive proof applications, explosive proof application transformers, and the transformers being used for a deep water like offshore. Okay, so deep water applications, this 60076 is applicable. So the 60076 is not really applicable for all these applications, and the transformer meant for this purpose is not really as a part of this 60076. Okay, so this is about the standards of the transformer. Hope this is clear. Any doubts in this?
No.
Yeah, it's fine, Venkatesh. These things we will discuss during the subsystem designing part, so you can go through to the next topic as well. Yeah, this already we have covered.
Have you already covered these things in your sessions?
Yeah, during the transformer topic, we have covered what the standard we follow for the transformer. So, yeah, you can go with the next.
Okay, right. Then I will directly jump into the ETAP and I will explain these concepts in the ETAP
Yeah,
itself.
yeah.
Right. Fine. Okay, now let me take a transformer here. One small transformer. Okay, coming to the modeling of the transformer, more specifically two-winding transformer for a load flow analysis in ETAP. So we will not go really in-depth parameter by parameter. Here we will focus on the modeling of the two-winding transformer, and further to two-winding transformer, how to give parameter by parameter. That is what we are going to see. So as I told you, ETAP uses the terminology primary and secondary, but it is not really ideal, or it is not advisable to use the terminology primary and secondary. Because of that, we have to use the terminology as HV and LV. So that is ideally it's better, right? So now let me connect this transformer to two different buses. Oh, this is 110 kV and this is 11 kV. Okay, fine. So now in this transformer, we can call this as a primary and this 11 kV as a secondary. Okay, but if we add any, suppose why we are calling like this, let me connect a load here. Right, I think this is the perfect application. So if you see this application, you see this transformer. So here the transformer, this is the transformer primary and this is the transformer secondary, right? That means 110 kV is on the primary side and 11 kV is on the secondary side. Okay, why we are telling like that? Because the power flow will be from this side, right? From 110 kV to 11 kV. So that's why we are calling this as a primary and this is as a secondary. But if suppose, if we add something like this, if I'm connecting a load here and connecting a source at this point, okay, if I connect a load here, so then your primary will be 11 kV and your secondary will be 110, right? Because the power flow will be in this direction. So generally the transformer is a bidirectional device without any constraints, and the capability of the transformer is a circle to an extent. So we cannot really use the terminology primary and secondary because power flow will be from bus 4 to bus 5 or bus 5 to bus 4. And it depends upon what is connected on the bus 4 and what is connected on the bus 5, right? I hope this is clear about the terminology of the transformer. Next, let me open the yes. So we need to here understand from here. Let's talk away some terminology. Instead of this primary and secondary, we can call it as a high voltage and the low voltage side. Then next, coming to the standard of the transformer, generally we talk about two standards. One is the IEC standard and second one is the ANSI standard. And you might have seen the symbols like this, the circles. If you see here, the circles. So this is a representation of the IEC standard. Whereas if you go through the ANSI standard, it will look like this. Yeah. So the transformer will be look like this. It will be look like this. So this is the representation of the transformer in the ANSI standard, and this is the representation of the transformer in the IEC standard. Okay. Because you might be studied in some textbooks with this symbol, right? If you use this symbol, that means it is following the ANSI standard, and if you are using this symbol, it means it is following the IEC standard. Okay, this is the first and foremost thing which you need to understand. Why? Because with respect to the transformer rating, why this understanding is important? Because with respect to the transformer rating, the IEC and ANSI defines the rating of the transformer in a completely different ways. Because IEC defines that the rating of both the HV and the LV winding remains the same. So essentially, effective loading of the transformer will come down. But as far as ANSI standard is concerned, the rating means the loading at which it can take, or the maximum loading that the transformer can able to handle. So that's why the rating, with respect to the rating, the IEC follows the different way, whereas the ANSI follows the different way. Okay. If you belong to the countries which follows the ANSI standard, probably Manoj, I think you are wait. Raghav, can you disable invitations?
You just stop sharing and again share. It will be disappear. Stop share and reshare.
Yeah, now are you able to see my screen?
No. Please restart. Please reset. Yeah, please reshare. Share screen. Please share again. How it is. Yeah, now coming. Yeah, perfect. Yeah, it's perfect now. It's okay now. Why is not coming? Venkatesh, why is not coming? I think muted somewhere. You are muted.
Okay, sorry.
Yeah.
So you should be a little bit careful what's the standard which you are picking up, whether it is an IEC or ANSI. Okay. So here I just came back to again the IEC standard, right? Right. And you need to choose whether it is the transformer is for the IEC as for the ANSI. So that is clear. Next is the connector is here. If you see here, the connection, whether it is used for a three-phase application or it will be used for a single-phase application. As I already connected this, so that's why this color, this is getting gray color, right? So I'm not able to edit this. Suppose if I bring a new transformer here, now if you see here, you have the option to choose whether this transformer can be used, whether it is a three-phase transformer or a single-phase transformer. Means you need to specify the transformer as for three-phase transformers, or here you can option to select three single-phase transformers. Okay, so that will give the another topic like the type of transformers. We generally classify this as a step up or step down, but it's not really true. It's a bidirectional reverse, right? And here you have a three-phase transformers versus single-phase transformers. It depends on the number of phases, and probably you might be aware that the traction transformers, which will be connected with two phases on the HV winding, whereas LV winding is phase and neutral. That is also another type of the transformer. Okay. And next, from the manufacturing perspective, if you see, you have like a shell type or a core type. And probably you can consider three-phase transformer and have the option to select the three single-phase transformers also. Right? Also, we have a center type of transformer. If you select the single phase, so you should be able to select the center type of transformers. So this generally will be used for the traction transformers, right? So like that, you have different type of the transformer applications you can select. So with respect to the first phase, as far as ETAP is concerned, you have to tell what is the HV bus, what is the LV bus, and you have to tell whether the transformer is in service or out of service. And essentially, you need to specify this standard. That is very clear. You need to specifically tell whether it is a three-phase transformer or a single-phase transformer. And in three-phase, you have like three-limb, core type three-limb transformer, core type four-limb transformer, five-limb transformers, etc. So, and you have the option to select three single-phase transformers also. Okay. Right. Next, can you just tell me where should we use these three single-phase transformers?
Mining.
We need this.
Mining industry.
Switching substations.
Any specific reason?
Like, yes, like ICTs.
Generally, these three single-phase transformer generally will be used where you are having a transportation issues and where you need the redundancy. So there you need these three single-phase transformers. Okay, right. Next coming to the rating phase here. Right. So here if you see,
Sir, how the redundancy is maintained in the single phase?
you are having three different transformers on different phases, right? Suppose if any transformer fail, you can replace with the spare transformer.
Okay, but that is in connection, or we have to keep it in store?
No, that spare transformer you will be separate. You will keep it separate, but at least
It is not in the humming condition, no? It is not
no.
connected,
It will
sir.
not be in the humming condition.
Yeah,
It will
thanks.
not be connected.
Okay, it is a spare standby.
Yeah,
Thanks.
right.
Sir, you said you were saying about transportation at the time of transportation. So can you explain with an example?
Okay, right. As I told you, suppose if I take a transformer which is of, let's suppose I am using a transformer for 660 megawatt unit. Okay. So in this, what is the minimum size of the transformer that is required? 660 divided by 0.85. So that is 776.47 MVA is the minimum transformer. That means the generator step up transformer that is required. Now, point here is developing this manufacturing this 776 MVA transformer. The size itself is a very huge, right? So you have to transport the transformer from the manufacturer to the site. So definitely the size of the transformer will be increased. So you will be having a transportation issues. So instead of transporting a large size 3-phase transformer, there what we will do, we will go for a 3 single phase transformers that is near about 776 divided by 3. So each transformer is of 258 MVA. Okay. So like this, these single phase transformers can be used where you are having a transportation issues. That's what precisely I want to highlight. Yeah, is it clear?
Yes, sir. Thank you.
Yeah. Right. Next coming to the rating phase of the transformer. Here we have to give the what is the primary voltage and what is the secondary voltage. Okay. And this is the rating of the transformer. So we need to ask the HV side voltage and LV side voltage both in kV, and we need to ask the MVA rating of the transformer from the transformer manufacturing data sheet. Okay. Next, let's suppose this is connected to 110 kV and this is again connected to 11 kV, and the rating of the transformer is, let's suppose it's a 25 MVA. Okay. Now, the derated, here you can see there is a factor called that is derated. So this is the derating factor will be applicable with respect to the altitude and the ambient temperature. Suppose if I change this altitude from 1000 meter to, let's suppose 2000 meter, let's see what happens. See, your transformer is got derated by 18.3%. That means even though your transformer is rated for 25 MVA, but because of the altitude, you cannot be able to use it for 25 MVA. That means you cannot be able to use it for the complete MVA rating of the transformer, or that it's rated MVA. So your transformer will be derated. That means you can use the transformer only up to 20.427. Okay. Similarly, let me bring back it to 1000 meters. That means up to 1000 meters, there will be no derating. So even though if you change it to 500 meters, so there will be no derating. If it is 800 meters, there is no derating. But yes, till 1000 meters, there is no derating. If you increase the altitude of the transformer from 1000, means the application where you are using, if the altitude is more than 1000 meters, so then your derating factor will come into picture. For 1500 meters, suppose if I use, this is the derating. 9.6% is the derating factor. Okay, right. Next one is, let me keep this to 1000 meter. I'm coming to the ambient temperature. Okay. So suppose you are using the transformer for the ambient temperature of 30 degree. So there will be no derating. But instead of 30 degree ambient, if I am using this for the 40 degree ambient temperature condition, then if you see the transformer will be derated to 22.61 MVA. That's why while giving or while manufacturing the transformer, you should keep in mind the ambient temperature of the location at which the transformer will be used. So that is most important. So if your transformer is designed for, let's suppose 50-degree ambient, okay, and if you are using this ambient temperature, that means at 50-degree, your transformer is derated to 20.448. Suppose you can take like this. You can take like this. Suppose at 50-degree, you have designed a transformer at 50-degree ambient temperature, which is of 25 MVA. And if you operate the transformer at the ambient temperature of 30-degree, you can definitely operate it more than 25 MVA. Okay. Similarly, if you operate the transformer at 70-degree ambient temperature, definitely the derating will come into picture. So it's not about the derating, it's the uprating also. Well, suppose here that ambient temperature is 30-degree. Suppose if I use this ambient temperature as 20-degree, so even the transformer derating is minus 10.5. That means you can use it 10.5% more of the transformer rating. Okay, so that's why this parameter should be very important when you are designing the transformer or when you are modeling the transformers. Okay, I'm coming back to 30. Next, coming here, you have the type of classes, like whether it's the liquid fill, dry type transformers that can be selected here.
So can you just, sorry to disturb you, can you just brief on the ambient temperature? If I have to use a 30-degree in the country like Oman, like that, and in the Gulf countries,
Yes.
so shall I go with the cooling system with the air conditioning the transformer room? And
Yes.
what is the effect of the air conditioning in the transformer?
Air conditioning in the transformer.
The transformer room. If I am using this transformer in the
Definitely. See, suppose you have manufactured the transformer with the consideration of ambient temperature of 30-degree. Okay. But if you are using the transformer, it's, let's suppose, for the ambient temperature of 50-degree. Okay.
Yes, sir.
So in that case, you cannot really able to extract the 25 MVA of the transformer. You can able to extract only 20.44 MVA.
Yes, sir. Yes, sir.
Okay. Now, as you are telling, if you put the transformer in the AC control room, and if you are able to maintain the transformer for the ambient temperature of 30-degree, of course, the ambient temperature, what I am referring it is as the room temperature also.
Yes, sir.
Okay. With the air conditioning system, if you are able to maintain the temperature of 30-degree, then definitely you can go with for 25 MVA. If you are able to maintain the temperature of 20-degree, yes, you can use the transformer up to 20.27 MVA also.
So my question is second one. I'm controlling the temperature of the substation. That's not an issue for me. But
Yes.
is there any humidity issue in that one? Says outside temperature is 50-degree and inside temperature is
No,
30
with the
degree.
air conditioning itself means you are maintaining the transformer, you are maintaining the ambient temperature.
Yeah.
Right. So as far as you maintain the ambient temperature of 30-degree, yes, you can able to use the transformer up to its full MVA, that is 25 MVA.
MVA rating and derating, I am clear. Is there any effect of the cooling system on the transformer? Means if a transformer is it's not oil cooled, it is a what you call it, dry type or
Yes.
like that one.
See,
So
if
is the
it's-
moisture effect in the terminal box like that? Has to check
Yeah,
for.
that is because of the that is because of your humidity applications, right? Means they depend upon the humidity. That's why in such cases you will generally, it is recommended to use the dehumidifiers. In the transformer marshalling box panels, in the HV terminal box, LV terminal box, generally it is preferred to use the dehumidifiers so that you will not get the moisture will not be accumulated on the transformer
Terminal.
terminals.
Yes. That was the thing. Thanks.
Okay.
So the selection of the dehumidifier is mandatory in that case.
Yes. Okay. Right.
Clear, sir.
Next is coming to the type of classes. So you have two different type of transformers. One is the liquid fill and the dry type. In the liquid fill, it is especially this is the oil fill. So if you select the different reactions, it means in the liquid fill, you have the option to select mineral oil, synthetic oils, non-flammable synthetic oil. Like for the ESP transformer applications, there you are using a silicone oil. So different applications means a different type of oils can be used for the transformer applications. But generally, mineral oil is being used for the transformers because of its high flash point. And next, coming to the cooling mechanism. here you have different options like ONAN, ONAF, OFAF. Suppose if your transformer is like ONAN, that means oil natural, air natural. Okay, that means oil will be circulated naturally because of the gravity, and there will be no separate cooling medium for that. So in that case, the transformer can be used up to 25 MVA if it is a 25 MVA rating transformer. But yes, if you are cooling it forcefully, then you can use this transformer up to 31.25 MVA. Okay, so you can use the transformer up to 31.25 MVA. Suppose if you are using the OFAF, that means oil force, air force. So in that case, you can use up to, again, here it will not much change. Let's suppose if I am changing it to 100 MVA. Yes. Oh, sorry, I have not selected the option. So, right. So now, if you see here, what is the oil natural, air natural? That means when there is no external cooling media, you can use the transformer of this 25 MVA up to 25 MVA. But if you are having a cooling mechanism for the air force, so you can use this transformer up to 31.25 MVA. Whereas if you are using another external cooling medium for the pump also, oil force, air force, that means you are forcing the oil to circulate as well as forcing the air to circulate across the transformer. So then you can use the transformer up to 39.063 MVA. Okay. So, and depend upon the temperature rise that is allowed 65 degree. So total temperature rise is 30 plus 65 degree, that is 95 degree. Whereas if you select the dry type transformer, here the temperature rise will be 60 degree. Okay. So here also you have different options. Where if you depend upon the type, if it is an enclosed type, non-enclosed type, depending upon the type of cooling classes, so you can use it up to 150 degree. So this is about the class of the transformers. Of course, you get these details from the transformer manufacturer. Next, coming to the impedance of the transformer here. So here you have to give the percentage Z and the X by R of the transformer. Generally, we will use this typical impedance Z and X by R. So this, as I told you, this ETAP uses this 60076 part 5 table 1. Okay. And next you are having a impedance variation as per this impedance tolerances. So as per this, the tolerances is as per IEC 60076. The tolerances has been given in the 60076 standard. So as per the standard, you can give the impedance tolerances. Next, here you have to give the no load data, like what is the no load, full load means what is the magnetizing current of the transformer or the no load current, and what will be the no load losses, positive sequence no load losses, as well as the zero sequence no load losses. But even though if you give the typical values, ETAP will do a balanced load flow analysis. In the balanced load flow analysis, ETAP will not use this no load data. It will be used only for the unbalanced load flow. That is one of the technical glitch of the ETAP. They will not use this no load losses in the transformer for the balanced load flow. Okay. Right. Next, coming to the tap here. So this I will explain when we are going in the tap. And this is the grounding option. So here you can select the type of grounding as per the transformer, like whether you are using it for the delta or star. So that you can select it here, whether it's a delta on the primary side or it's a star on the primary side, how it will be, whether it's a primary means it's a star connected on the secondary, on the star connection, how it will be, the grounding will be, whether it's a solid grounded, resistance grounded, reactance grounded, whatever it may be, that can be selected.
There has been power cut at Venkatesh, so uh, please wait for 5 minutes. He will join again. Okay.
Okay. Raghav sir.
Yeah,
Sir, I have one query about the transformer, sir. Can I ask you, sir?
yeah,
Sir, in the distribution field, in the discoms, like a transcom, sir, they are using the 8 hours the three-phase power and another 16 hour use the single phase power, sir. They use the load dispatch the transformer type. They are telling like that. Sir, you about knowledge about this type of the transformer, sir? They have to convert the.
Harshit, sorry, it's not clear to me. Just hold on, actually. Few students not able to join the meeting, so I'm assisting them.
Okay, no issues. Okay.
Yeah, hello.
Yes, sir. Hello.
Yeah, Nilesh, hold on. Actually, there is power cut at Venkatesh's location, so we are waiting for them. When he will join in 5 minutes. Have some patience. Suraj, are you there? Suraj Yadav, are you there in the meeting, in the class?
Yes, sir. Yes, sir. I have joined.
You are joined since beginning, right?
Yes, sir. Yes, sir.
You know that why we have stopped the meeting. Already communicated you that Venkatesh power cut at Venkatesh locations. So I have patience, okay?
Okay, sir.
pausing the recording because he's taking time. So I'll pause the recording.